vais juste vous présenter donc Marc Bowick, qui est professeur à l'université de Santa Barbara. Il est sous-directeur de l'Institut de physique théorique qui s'appelle KITP à Santa Barbara. Et donc on est très content de l'accueillir pendant un mois à Paris, au Collège de France. Et il va faire 4 cours. Le thème général du cours, c'est en anglais, Order, Geometry and Defects. Marc est un très grand spécialiste de la géométrie et des défauts en physique. Il a travaillé sur des tas de choses, sur la physique des particules et de la physique théorique très très formelle auquel je suis obligé de dire que je ne comprends pas grand-chose. Mais depuis plusieurs années, il travaille sur la matière molle et certaines applications à la biologie. Donc c'est un peu ça l'axe des cours qu'il va faire ici cette semaine. Donc il y a 4 cours. Il faut faire attention à l'horaire. Il y en a un qui est un mardi au lieu d'être le lundi. Mais autrement, ils sont à 2 heures, tous dans cette salle. Ce que je dois faire avant que Marc commence, il y a une tradition au Collège de France, c'est que les professeurs invités reçoivent une médaille. So Marc, here is your medal from Collège de France for invited professors. You have to be careful when you take the plane with it. You might have problems, especially now. So thanks a lot for coming, and we are all looking forward to listen to you.
Thank you, Jean-François. Thank you. Can you hear me okay? Yes. Oh, thank you, Jean-François, for that introduction. Sorry, the talk is not in French. I think I could manage Italian, but I'm going with English. It's just wonderful honor to be here, particularly in a country and city that really celebrates intellectual achievement. Arrived on Friday and took Rue Lagrange to Rue Monge, all around seeing the celebration of scientists and writers, creative endeavors. I think I'll be now very conflicted. I won't know whether I can use Monge gauge or conformal gauge, but Monge is going to be ever present, I think. I want a series of lectures on different topics, but they all have some things in common, which are geometry, how geometry can be exploited or is used to produce unexpected, counterintuitive behavior, unusual states of matter, unusual ground states, and drive and control, not through like external fields, but through geometry itself. So symmetry and order are very inversely related. Normally, when you think about order, if you read any book on order, it will show you beautiful pictures of things like crystals and gemstones. But those are things where order arises from breaking of symmetries, from reductions in symmetries. Generally, the most symmetric things would be random, and they would have very little structure, very few features. So when you reduce the symmetry, we usually call it breaking the symmetry, that drives the formation of structure. So they work inversely, and it can take a while to wrap your mind around that problem. A lot of our problems in physics are not reduce, but are problems in analysis. You have some functional, some function, some Hamiltonian, various settings where you're trying to, say, find some extremum. And the properties of that extremum can be very different from the initial kind of data, the initial setup of your problem. And so I want to start with one very simple, discrete example of this. I'm going to use the blackboard, but you can also see some things up here. So supposing we start with just a square. Okay, so we're in 2 dimensions. 2 dimensions turns out to be remarkably rich, complex enough to have, big enough to have interesting complexity, but not too big so that you can do anything. So there's a problem known as the opaque square problem. Imagine you have this square and you want to prevent, say, design a mirror in the plane that will block light that goes from one side to any other side. It has to block all such paths. And you are interested in a particular kind of path, not any path or graph on the surface, not any one, but the one that minimizes the length of the graph, okay? Length of the mirror, 1 dimension. So, and you start with a lot of symmetries, right? You start with 4 rotation symmetries and 4 reflection symmetries. So 8 discrete symmetries in this problem. And generally, it's drilled into us, at least to me, in learning physics and mathematics and so on, exploit all the symmetries of the problem. They should somehow make it much easier, reduce the degrees of freedom, tell you what kind of answer limits the answers that you can get. So let's look at this problem. Again, we want to minimize the length of such a graph or mirror. So of course we could go around all 4 sides. That's length 4. And we wouldn't really do that usually. But of course 2 diagonals will do it, block any path. You can also think that you're trying to locate a cable that's in 2 dimensions, and you have to, the cable goes from one side to another. You want to locate it with a minimum length trench that you're digging. So this one has length 2 times square root of 2, 2.8. And then if you've ever played with soap bubbles, minimal surfaces, or things like that, you will think of putting more than one interior point in here. So you do something like this, right? That's what soap bubbles would do. And this object has length, it's good there. Nice rational numbers, nice numbers come up in here. 1 plus square root of 3, that's smaller, 2.732. The question is, what is the minimum length object like this? And the answer is the following. Notice that you have some fewer symmetries here than the 8 that you started with, but a lot of symmetry. And the answer is really somewhat counterintuitive, and that is that you put one vertex in the middle. Vertices in graphs traditionally discovered by Torricelli, put an interior vertex. But, another one here. This is the minimum length structure. And notice crosses, it blocks light going from one side to the other. And the incredible thing about this, at least to me, is first of all, the topology has changed. You have now 2 disconnected pieces, the most basic kind of topology you can imagine. This is all connected. This is 2 disconnected pieces. And you have this isolated coordination number 1 vertex in the middle, coordination number 3 vertex here. And this length, it's a nice number, 2 plus square root of 3 over 2 here. That's 2.639, considerably smaller. So this has only 1 of the 8 discrete symmetries we started with. So 7 out of the 8 are broken. So 2 dimensions, a simple problem with emergent non-trivial geometry and topology. Another example and I will be talking about shape here and systems that develop sharp structures from very smooth-looking initial problems. And this problem is called the minimal resistance problem. You just have a projectile, like a train, moving through very, very low density air. You just have one molecule bouncing off the front. And you want to ask what the shape of that front, the front of your train projectile, what shape minimizes the drag. This is a problem studied by Newton. It's in his Principia towards the very end. And it's just geometry. And you look at momentum transfer of one molecule bouncing off the front. And you compute velocity squared. That gives you a drag coefficient. So if you translate this problem, which you can do, I'm not going to do it here, but into a problem in the calculus of variations, then the object that you're minimizing here to minimize the drag is this functional. You're integrating over a disk 1 over 1 plus this gradient of this profile, u of x. X is in the plane, squared, gradient squared. So you can see here that it might be good to exploit a few places where the gradient is very, very large, even singular, even divergent. That gives you a very small contribution to that drag coefficient. And Newton solved this. He did it geometrically. Also, I think he knew the calculus of variations, but this formulation is one of the earliest introductions of calculus of variations in physics. And he found that you want to have this kind of flat nose to the projectile. And you can see the gradient at that point here diverges around here. Okay. So that's interesting. The problem looks very, very simple, very uniform, but the solution has, this sharp ring here where it goes flat. Newton, the original functional that you're minimizing here is rotationally invariant. And Newton assumed rotational radial symmetry for the solution. But there was, at that time, or for quite a long time, there was no proof that the graph U that minimizes this functional be radially symmetric. And later it was proven by Kavli and collaborators, actually, that if you look at this functional, there's a negative direction you can go to minimize it, which is not radially symmetric. And this problem is actually studied here in Paris, early 2000s, by Lachon-Robert and Pelletier. And they removed this assumption of radial symmetry. And they found really remarkable sets of minimizers. It's a function of the aspect ratio, namely how far out you go to the tip of the nose compared to, say, the length. And plotted here are their solutions. It's drawn so that it's what you would see if you're looking down on this object here. And this is the functional that you're minimizing, the value of the minimum resistance, and this aspect ratio. So the aspect ratio is going down as you go down here. And what they found is a series of solutions with very sharp kind of polygonal structures. Newton's solution is up here. As you drop the aspect ratio from 2 down to 1.5, you get a chisel-like shape, very sharp edge here, one edge. You go down further, you get a triangular face. You go a bit further, square face, and so on, pentagon, hexagon, n-gons, all the way down. So here are really non-trivial, polygonal, sharp faces in the solution, and you can see, plotted along here's Newton's solution, in the solution of this very, very simple-looking, rotationally invariant problem. And I will discuss a physics setting where sharp structures like this can emerge. Any questions? I welcome questions throughout, so. Okay, good. So the problem we're going to talk about, and actually it came out of work from Minwee Lee's group in polymer chemistry. Around 2007, I was here on sabbatical, and Jean-François mentioned this interesting thing that they found, sharp structures in polymersomes. So this is sort of the origin of thinking about this kind of problem. So imagine we have a two-dimensional system with liquid crystalline order. And we are trying to minimize the energy of this system. The energy is going to have two major components. It's going to have a liquid crystalline piece here, and it's going to have a bending piece. This bending piece is a mean energy term. I'll discuss that in a minute. And the problem is you have some field, in this case it's a director field, an order-like field, living on this system, and it's on some manifold, some two-dimensional surface, which you want to determine as part of the problem, not only the structure of the order field, but actually the surface on which it should live. And the functional itself, the energy in the order field and the energy in the bending, depend on the surface, on the structure. So you have sort of a multiply infinite kind of functional to extremize. You not only have to minimize the energy on some fixed surface, you actually have to determine what surface you're on. Okay? So that is asking really not only what the liquid crystalline order is like on the surface, but what shape it should adopt to minimize this energy. So we can say, ask things like, how does the Hamiltonian or the energy functional determine shape? What can we learn about an energy functional given the shape, and how are these two things kind of connected? What are the contributions here? So the liquid crystal energy, it's two-dimensional liquid crystalline physics, so we have a director field N here. Director fields are very actually kind of subtle fields because they are orientations. They are line fields. There's no vectorial direction. Okay? This means that you're working on a projective space. So the geometry is really projective geometry. It's the manifold is, since we're in two dimensions, the manifold is a circle. That's the value of the order parameter. Modded out by inversion. If you think of it as a vector on a circle, we have to mod out by the vector n going to minus n. That's what makes it a line field. So don't think about directions. So that space is RP1. And the contributions are just two-dimensional gradients. So we have a divergence term and a curl term. So this term here is associated with splay of the field, like this, and this term is associated with bend of the field. In two dimensions, the term corresponding to twist you'd have in three dimensions vanishes identically. And then we're integrating over some surface sigma to be determined. So we have to determine, and there are coefficients here. So there's a coefficient I will call K here, a parameter or a modulus, if you want, a Frank-like constant here. For a moment, I'll just put this, well, in general, we can have two ones, K1 and K3, associated with splay and bend. That's the liquid crystal piece of the Hamiltonian. And then we have a piece which, so this is just intrinsic energy of a liquid crystalline field on some two-dimensional surface. But since this surface lives in three-dimensional space, if we want to know something about the shape that doesn't depend on intrinsic curvatures or geometry, It depends on how that space takes shape in the bulk 3 dimensions. So corresponding here to that piece, shape deformations of the Hamiltonian, is a piece which is the integral over the surface of the mean curvature squared of the surface. And anyone know who discovered this term, form of this term? So this was actually discovered by Sophie Germain around early 1800s, 1811, before the development even of elasticity and the associated differential geometry and so on. This coefficient we call bending rigidity, kappa. So we have kappa, K1, K3 are moduli in the problem. This was a problem in bending and describing the patterns of the Chladni plates that she was trying to solve, and she won a prize from first class of the Institut de France for her solution to this problem over 5 years, 3rd attempt at this prize. No one got it before her. Yes? Yes.
If the surface itself had some torsion, wouldn't there be twist? If you imagine you have a surface with some order overlaid, and the surface is twisted.
Yes. So in here, these should be covariant derivatives. I should have written it as D. So this D would have the ordinary derivative piece and a connection piece. And you're asking whether this connection piece could have torsion. So that's possible, but I'll be looking at the case where the metric is covariantly constant and there's no associated torsion of the connection. I don't actually know if that will change the solution to this problem, and I don't know physical realization of torsion in this connection. Yeah. So I'll be looking at ordinary Riemannian differential geometry on this surface with the ordinary derivative, how things move, and then how things change because you're on a curved surface. Even if they're constant here, they will change by virtue of the fact you're moving around on a curved surface. So you can say it's a special class of, well, Riemannian geometry without torsion. If it was torsion, the metric wouldn't be covariantly constant, or you'd have to modify it. Yes?
The surface has a magnetic field on top of it.
Yes. This is N. In 2D.
If you bend in different directions, it won't bend the same way, no? No, the kappa is the second one.
Yes.
It should be a tensor and not a number.
Yes. In general, it will be a 3x3 tensor. You can have bending rigidity different depending on how you bend. Yes, that's true. I'll take the simple case where that's uniform. It won't change the favor of the solution, but yes, there are 3 different bending rigidities here. Kappa. Yeah. So I'll take one parameter case. No asymmetry there in its bend. And I'll take the mean curvature 0 here, so I'm looking at the symmetric case, 2 leaflets that are symmetric, no difference between the outside and the inside. So H0 is 0. So this object that Sophie Germain discovered is the sum of the principal radii of curvature at any point on the surface. So some curvature this way, some curvature in the orthogonal direction, and you add those up and you square it. So if you look at the associated force law, it's proportional to h, the mean curvature, and that was the hypothesis of Sophie Germain. So I will look here at 2 special cases. Okay? I'll look at the case where K1 equals K3, so-called 1 Frank constant approximation in the liquid crystalline theory. So the cases are K1 equals K3, and then I'll just call this K. So that liquid crystalline energy just becomes K. K is the modulus now. K, integral of the divergence squared term. and the curl term. So in that case, this just becomes K integral over the surface to be determined covariant gradient of n squared. You just add these up and you get this. So this is what we would call a nonlinear sigma model. It's just the gradient, but of the line field n of unit value. That's just the choice. So the complications are you need to determine the surface, you need to determine the metric, because that contributes to the covariant derivative. And then the bending energy, I called it Sophie Germain, has the kappa in it. It's the same. Integral over the surface of h squared. H is the covariant, it's a vector in 3D, and it has in 2D two indices. It's the covariant derivative of a tangent vector, d beta x. And x is the embedding, a map of the surface into the bulk space, which we take as flat Euclidean space. If the surface has a boundary, a hole, it was shown a long time ago by Helfrich, that that hole would spontaneously close in the ground state because this piece of the Hamiltonian is scale invariant or conformally invariant. And a line tension, a hole would contribute a line tension which grows linearly with the system size. So when the system is big enough, the ground state prefers to close up that hole, and therefore we can take as the topology the two-sphere, no holes, simplest Riemann surface. Okay, so that's already some progress. And then we will look at two special cases of this problem. The bulk modulus K is an energy, and the bending rigidity is an energy. So the dimensionless parameter modulus in this problem is K divided by kappa. So the cases will be one is this K over kappa is much less than 1, and the second case will be the opposite. K over kappa is much bigger than 1. Okay? So in this case here, case 1, I call kind of rigid case. This is the limit, say, in the bending rigidity is very large compared with the cost of distorting the liquid crystalline energy. You can take even kappa going towards infinity. In that case, extremely rigid to bending, it will like to be the perfectly round two-sphere in that limit. So we know that sigma in the ground state, we're just talking about ground states here, so we're only solving a small part of the problem. But the ground state will go towards, as this goes to 0, a perfectly round two-sphere. And this functional, in that case, is known as a Willmore functional and is studied, very important functional in mathematics. This is the case I'll mostly focus on. So this is the limit where the liquid crystalline deformations are dominating the physics. Okay? So that means that we, first of all, need to focus on minimizing that liquid crystalline contribution. And the other case here, an equivalent case really is the case, say, one of the moduli K3 goes to infinity. In that case, there's no bend and only splay. And then if I take the level set orthogonal to pure splay, it looks like this. So this is a layered structure. So I can take K, also called a symmetric or ridge system. I can take K as just K1 left over in the limit, K3 goes to infinity. So both cases are treated by this analysis here. We'll just determine it, just changes how you interpret K. So we have a ridge system, or we have a liquid crystalline system with Frank constants that are equal. Okay, now in this case, so we have to focus on minimizing this liquid crystalline energy. Those are the two cases. So what do we want? In here, since we have curved derivatives of n, we want the liquid crystalline field to be uniform, like it would be in the plane. But we also want the metric to be, we want it to be flat in terms of the metric on the surface. So you want uniform liquid crystalline order on a flat surface to minimize this liquid crystalline contribution to the energy. But we know that's not a solution of the problem, because our topology is the two-sphere. So the integral of the Gaussian curvature, I'll call it R, over the surface is a constant. 1 over 2 pi times this is the Euler characteristic of the surface. So this is some non-zero value, like 2. Okay? The Gauss-Bonnet theorem. So we want the Gaussian curvature, this non-trivial metric contributions in the covariant derivative contribute to the intrinsic curvature of the surface. We want that to be 0, but its integrated quantity is highly non-zero. So this is an obstruction to the naive kind of ground state for this system. So the solution is to make it flat as much as possible. And you can do that if you have a faceted structure. So you have flat faces, but a global non-trivial topology of the two-sphere. This means that the Gaussian curvature contributing to this non-zero integral here will be isolated singular points. You concentrate it all at some vertices of this faceted polyhedral shell-like structure. So we want singular points for the Gaussian curvature, and we want also to determine what kind of polyhedral structure we should have. Now, two important things now come in. We want to have a non-trivial surface defined in this problem. So that means that in order for it not to be degenerate, we need at least, we need really 4 non-trivial points, otherwise we can draw, flat, degenerate structures through the surface. So we want at least 4 vertices where we concentrate this Riemannian curvature. So that suggests that we should try a tetrahedral shell, 4 faces, 4 vertices, and the edges, the 6 edges of the 4 edges of the tetrahedron. It could be any higher faceted-like structure, face-wise flat. So the minimum would be 4 vertices. And on that structure, we can just look at the discrete net for that structure, which looks like that. We can fold this up into a tetrahedron, or unfold tetrahedron into this flat space, and then we can draw a uniform liquid crystalline order on the surface. Straight lines. So liquid crystalline energy is identically zero. It's flat and uniform. And here's such a structure, and you see you just fold it up like this, usual way, to make a tetrahedron, piecewise flat, uniform curvature on each face, uniform order on each flat face. It has 4 vertices where the Gaussian curvature is singular. On top of that, we know that a line field on the surface with the topology of the two-sphere also has to have some zeros, cannot be non-zero everywhere. Again, a field living on the surface, the classic case is a vector field living on the surface. A vector field living on a two-dimensional surface has to have zeros where the sum of the winding number around the zeros, or the index, has to equal the Euler characteristic of the surface. So for a vector field, that means that the sum of the indices of the field, that's the places where the field is 0, and you compute the winding number around each of those zeros. This has to be the Euler characteristic, which is 2. So that means you can have 1 zero of index 2. That would be a dipole. People often say they have to be at least 2. No, it's not true. It can be 1. 0 of index 2. 2 zeros of index 1. That's the more common case. So it's a north and south pole. You have sinks or sources or vortices or asters like that. Index 1 here, and index 1 here sums to 2. That theorem, which is the Poincare-Hopf theorem, you can think of extending that to the case of a line field, which is different, by the fact that you can break up a index 1 vector field into, so this kind of object, into 2 objects that look like this. So in a structure like this is a defect for the line field in 2 dimensions. And if you go around, take any contour going around this defect, then the line field rotates by 180 degrees, which means it comes back to the same field. And the index in this case conventionally is described as 1/2 because you wind 1/2 of 2 pi to come back to itself. And so this is basically 1 going to 1/2 plus 1/2. An index 1 field in the liquid crystalline case would normally decompose into 2 1/2s. I actually haven't seen a rigorous proof of Poincare-Hopf theorem for a projective field, but I'm sure it can be, pretty sure it can be done. But intuitively, you can see that this should happen, which means that the sum of the indices on the zeros of this n, this is usually called strength of this pneumatic defect or disclination, the sum of the strengths, S or indices, at each of the zeros should be, again, the Euler characteristic 2, which means, with the basic quantity being 1/2, which means we could have 1 index 2, 0, 2 index 1, zeros, or say 4 1/2s. In 2 dimensions, the possible values of these indices are determined by the first homotopy group, pi1 of RP1, This topology is S1 but with points identified, so it's really half of a circle with this identified with this. So this has the same topology as the circle. So the pi1 is z. So the indices are integer multiples of the basic defect. So any multiple of 1/2, plus or minus is a possible 0. Let's look at the elementary defect here. So we need 4 of those. So that suggests the obvious thing, that we should put the 4 zeros for this field at the same point where we've concentrated the Gaussian curvature. So you can think of this as 2 kinds of a disorder. One is the singular Gaussian curvature. The other is the 0 of the director field, which means it has a diverging gradient. So a singularity in the gradient or a 0 of the field. So I like to call this misery loves company. Concentrating disorder at the same places is often a very nice solution to this kind of extremizing problem. Now you'll see here, if we do this, that's a postage stamp with Sophie Germain. There's a very nice article in the archive by Holmes that discusses the history of Sophie Germain's contribution to this problem. The prize was 1816, and why we should call it, we usually call it a Helfrich Hamiltonian in self-matter. It should really be Sophie Germain Hamiltonian. We passed by Lycée Sophie Germain yesterday on a walk. Okay, so I argued that the solutions, because they want to be flat, should be what are called developable surfaces. So you just take anything in a flat sheet and you bend it without stretching. And with the uniform nematic order, that will give you a faceted polyhedral structure. So we've already learnt, just by minimizing this problem, that we get nice looking original problem, a very sharp kind of solution. Extremely sharp, 4 sharp vertices and edges. And you'll see that if you look at these uniform director lines on this surface, this is shown here, that around each vertex, this is the structure of the nematic field, goes along, turns 180 degrees at the defect. So this is exactly a discrete flat form of this 1/2 defect. That happens at each of these vertices. So that's nice. 4 defects, so to speak, 4 pieces of the Gaussian curvature gives you a ground state for this problem. So we've determined the shape and we've determined the director field on that surface. Highly, at first sight, a highly non-trivial problem. You can count the dimension of the solution space for this system. So we have 4 points in R3. So that's 12 numbers we need to specify the vertices. There are 3 translation and 3 rotation symmetries. That takes away 6. There's scaling because the bending energy here is scale invariant. So that takes away 7 of the 12. That leaves us with 5 dimensional space of possible tetrahedral that will solve this problem. But if we then add the fact that each of the vertices is this nematic defect, that means in flat space, the sum of the angles around these 3 vertices should be 180 degrees. So that would suggest 4 additional constraints. But if you write it down, sum up these angles, they're not all independent. There are only 3 independent ones. So that leaves you 5 minus 3, a two-dimensional space of possible tetrahedra that will emit this ground state with the zero liquid crystalline energy, except at the defects. If we take, and they correspond basically to the structure of the triangles on each face. We can have non-trivial, non-equilateral triangles that make up this faceted structure, this tetrahedron. If we take the extreme limit of the bending rigidity 0, that means there's also no, that means, well, okay. The bending energy here is non-trivial across a edge. The mean curvature has a dihedral angle as you go across an edge. So it's proportional to the energy is proportional to the length of an edge. So if you take any non-trivial bending rigidity kappa in this limit, then you want to minimize the sum of the lengths of the edges. So that will give you a perfectly equilateral triangle for any non-zero bending rigidity in this regime where K is much bigger than kappa. If you go all the way to zero bending rigidity, then you can emit non-equilateral triangles on the face. So you have two independent angles, if you want, in the triangle. Any questions here? Yes?
First of all, there is defects that you didn't write. 1/2 plus 3/2 would work as well.
True.
Is there any reason why?
So this case, and this case would only give me would give me two defects. So it would not correspond to a non-trivial number of vertices to determine the shape. But the only actual reason for excluding these is that if you look at the contribution of the defects to the liquid crystalline energy, since they do contribute at the vertices, this is proportional, since you have a gradient squared, this is proportional to the strength of the defect squared. So a +1 or a +3/2 would be 9/4, and this one would be 1/4. That's greater than 4 1/2, which is 4 1/4. Now that's an energetic argument, and that fails in the ridge case. That fails in the case where you have just this layered structure, only splay, pure splay, or the level set is ridges. In that case, the energy of a +1 is equal to the energy of 2 1/2. So all these things will all become degenerate then. So in that case, you could have just two defects. You could have all these possible solutions. But you would have to have a non-zero contribution at the other missing vertices. And I think you won't get zero liquid crystalline energy on the faces in that case.
The other question is just a reverse one. You consider tetrahedra, you could consider octohedra, dodecahedra, and stuff like this.
Yes.
Do they have some stability in any case? Or
Those cases,
to a sphere, for instance?
yeah. Those cases do not admit uniform liquid crystalline energy because of the basic symmetry of the nematic defect. But if we change the symmetry of the field in here to a higher order symmetry, so vector field has invariance under 2π rotations. We can go to things p-fold-like structures that have invariance under 2π over p rotations, maybe p-fold symmetry. So if we increase p, for example, let's take p equals 3, okay? 3-fold order. Then in that case, it's the basic defect will be 1 over p, and we want to sum n of these up to make 2. So in the 1/3 case, we would want 6 vertices. So that would give you an octahedron. If we take p equals 4, that's 4-fold symmetry. That will give us 8 vertices, which is a cube. So you have to look at the order on the face. So if you have the order on the face looking like this, triangular, then that will give you the octahedron with this order on each face. And the fourfold symmetry case would give you fourfold order on the face, namely like that, and then you build it up to a cube. So by generalizing the nature of the order field, you will get all of these higher polyhedra. If you try these higher structures with pneumatic order, I think you could do it, you would change the strength of the defects at the vertices, and it wouldn't be the minimal solution. But I think you could do it, but these occur naturally when you increase the order of the field. Yeah, good question. Other questions? Yes, so that was, that question is good because I was going to discuss that later. Now, I said that this was motivated by an experiment in making polymersomes, which came out of Min Li's polymer chemistry group at Curie at the time. That's the original reason we started thinking about this problem. And their system is made from block copolymers. So lipid-like amphiphilic structures with a polar head, which is PEG in this case, and a hydrophobic block, organic molecule. But to build in the pneumatic order, they used systems that have pneumatic mesogens that hang off this hydrophobic chain here. Now, quite remarkably, and I don't think there's a really good explanation of this, although you can draw the geometry, that will fold up into a polymer vesicle with in-surface pneumatic order. So that means all these chains have to line up so that you have this two-dimensional liquid crystalline order induced by these mesogens hanging off the hydrophobic block. No one has proven, actually, that this should be the, say, lowest energy structure for this kind of arrangement. How this actually occurs, here's a picture of it, and it's kind of natural. The mesogens have to kind of stagger along here. But the fact that they can order into two-dimensional pneumatic order on the vesicle is really remarkable, and you might say that's very unlikely, but actually they showed that this system is a polymersome with liquid crystalline order. You get shapes like these round ones. This corresponds to the first case I was considering, where the bending rigidity is dominating. Okay? So you get roundest kinds of structures. You can get cylindrical-like structures with a baby universe round structure hanging off the edge because it's ordering first here and then later here, and so on. But they also found structures like this. This was the original problem that Jean-François mentioned to me. And they saw structures with these sharp kind of vertices. And in the interpretation I gave, this is one face of the tetrahedron where the edges are not straight because you're in some kind of intermediate regime where you have some contribution from bending and some contribution from the liquid crystalline order. So that is nice. You can have nanotubes as solutions to this problem also, because you can just draw ridges across here. But you can compute the energy in this case because now you have non-trivial bending energy along here because one radius of curvature is 0. Principal curvature is 0, but the other one going around this way is 0 going around this way is non-zero. So you get a contribution which goes like 1 over the diameter of the cylinder, and that contributes to bending energy 1 over r squared, and then it's spread out over the area. So you'll see this grows as the area, this grows as the area, and the tetrahedral energy is just proportional to the lengths of those edges. That's the only place where it's bending. So that's a length which is square root of area. So for sufficiently large area, the tetrahedron will always win over the nanotube. But this is a possible geometry for this system. So you can also get cylindrical topology in this problem. Now, this question that came up earlier, if we think of the ridge system solution for this problem, I call it here symmetric. It's not really a symmetric. Just think of it as layers, ridges. Then the reason why the energy changes in that case is in the case where K3 goes to infinity, that means we want the curl to vanish. So we only have the divergence contribution. That means that you can translate this if you write this down. That means the covariant derivative of n along n is 0. So this means it's what's called integral curve. It's covariantly constant along itself. Okay? So now if you draw integral curves for this case, you get structures like this. Right? And if you take the case, so you just draw your parallel ridges on the sphere, and then you look, say you take the solution where you have a +1, just 2 defects, a +1 at each end, and you can just cut it along one great circle, one equator, and you can rotate it by any angle you want. And that is another equally good integral curve on the system. So you go to this kind of structure. The +1 here is just moved by some angle from here. This is another perfectly good integral curve. So that means that the +1 would be +1 where these coincide is equal in energy to the 2 1/2s. So the energetics here changes from the pneumatic case, K1 equals K3, by having a ground state which is, say, 4 1/2s along one great circle. And now they're coplanar. Okay? So that's a different geometry from the case of one Frank constant approximation case of pneumatic order. So the ridge-like order has a different kind of ground state. So this is a zero energy deformation of the system by cutting and doing surgery. There's a different view of it there. So that's when you can have equally good use of +1s in the ridge system case. Even when you bring in the energetics, it's a bigger picture of this. So now this was the answer to Jean-François' question earlier. Let's generalize to p-fold-like order in the system. So invariance under rotations by 2 pi over p. P equals 1 is the vector case. Realizations would be magnetic order on the surface or ferroelectric. People have ferroelectric liquid crystals now. Tilt order, if you have a vector field in the bulk projecting out of the surface. If you project onto the surface, it will give you a vector field. So tilt order will give you vector order on the surface. The defects in this case are vortices. And the possible, now let's think of these defect sites as distinguished places on the surface, places that you could functionalize or use to make bonds that join these things together as analogues of atoms. So the number of defects on the surface would correspond to the valence in regular chemistry. If you have pneumatic order, that's the case I discussed. So you can have those solutions I described, so you can have valence 1, 2, 3, or 4 objects. If you take the triadic order, you can make with colloids. That's the 1/3 case is the basic defect I suggested. That gives you the 6 vertices, so an octahedron. Tetradic order, 4-fold order on the surface I'll discuss in my third lecture, where a developmental system develops in the order of the tissue, if you want, 4-fold order. Here, that would give you 8 vertices, so the cube. 6-fold order is the case for a crystal. So I call this hexadic. This would give you 12 vertices, so the icosahedral-like structure. And this was actually seen as, and these are the shapes, okay? Tetrahedron, octahedron, cube, icosahedron. I put as an open question here whether you can have 5-fold order in these systems, quasi-crystalline-like structures. Have no idea. These are the structures that you would get. So now, the virtue of these is that if you want to do chemistry with these systems, you have a very limited number of atoms, order 90, with as your building blocks to make molecules, and then bulk molecules or materials. Here, we can use an enormous variety of, let's say, mesoscopic building blocks, and we can have a very well-defined valence that will give you the order of bonding. So that will determine the kind of bulk molecules you can get. So this is a whole very rich ground for supramolecular-like chemistry, only partially exploited. Here are some realizations from nature of this kind of structures I've been talking about. If you look at the HK97 bacterial phage, you'll see this kind of hexagonal structure I talked about. Adenovirus 40 has an icosahedral structure. So this is the crystalline-like case, a spherical-like crystal. And you'll see that at the 12 vertices of the icosahedron, the system, the biological system, functionalizes those defects by attaching fibrils. There are 12 fibrils in this system coming out of the core of each defect. And this is how it can attach to a cell. So attack a cell, attaching the fibrils. So there's biological functionalization of this structure. In 2001, Monique Dubois' group in Saclay, they looked at cationic, anionic, salt-free mixtures, and they saw this icosahedral structure. Now, here's a picture there, looking down on the face. The beauty of this one is that how does the system deal with the zeros of the field, of the crystalline order? It doesn't actually put a defect there. It actually does surgery and punctures holes. Here, there's a hole. Nothing there. So that's like, if you want, it's like a big defect. So here you have 12 holes on the surface. So you have a system with Euler characteristic 2 minus 12, minus 10. A highly non-trivial structure where biologically, not biologically, naturally, you have done surgery on the system, puncturing each defect to make a hole. That way you can deal with the non-trivial topology of the surface. And these holes, you can get in or out, or you can functionalize or do stuff here, make 12-fold coordinated molecules and bulk materials. The case of pneumatic order with the 4 defects suggests valence 4-like structure, which would be the analog of tetravalent bonding in chemistry, sp3 bonding in chemistry. That's a natural structure to make diamond-like materials. So there's been a big effort in colloidal-like chemistry to make an object with this distinct characteristic 4-fold valence. And it's actually achieved to some level by NYU group of David Pine and a large number of collaborators, 2020 Nature paper. They make sticky kind of colloidal particles with 4 distinct patches corresponding to these defects, and you can make, so you can attach 4 objects to the colloid in the middle, and then you can hope they get some way towards having the right orientation of the neighboring superatoms, I like to call them, to bond up into the particular tetrahedral arrangement, which is somewhat staggered, to give you a diamond-like structure. This is interesting because such a system has gaps where light cannot propagate, photonic band gaps. So it's an analog of an electronic material with energy gaps, band gaps for the electrons. So there's a light manipulating like structure, and the numbers are such that diamond-like structure is very good for a photonic band gap system. In the case where you have, going back to the pneumatic case, with 4 defects, in a paper with Andreas Bauscher's group, 2014, we showed that this is an active system. Okay? So the defects are motile. And what happens is that the defects move, 4 defects on this active vesicle, spherical topology. They move from a tetrahedral structure, I discussed, to the structure of 4 defects on the great circle, through to the inverse tetrahedron, and back as a clock with the periodic frequency that's controlled by the activity and the size of the vesicle. So you can make, here are the oscillations of the system. This is the basic defect. You can make a biological or an active vesicle clock from the system, from the cycling of the defects. So it's something like, in the maser, the nitrogen molecule tunnels through from one site to the inverse site on the tetrahedron. Okay, so I hope I've convinced you that sharp structures can emerge from very smooth-looking problems. There's a lot of structure that can occur there, and it can lead to a wide variety of subsequent structures with these kinds of objects as building blocks. And if you're confronted with a problem, you should be careful about assuming the solution has any even of the symmetries of the initial problem. So look for solutions that violate symmetries. They could be there, and they're there in many interesting cases. Okay, I'll stop there.